All right, we are now experts at sequences. Now the question is, what do we do with sequences? And in calculus, what we do is we add them up. And you might say, wait a second, if we take an infinite sequence and we add it up, then are we going to get infinity? And the answer is very often yes, but not always, which is interesting. This harkens back to your improper integrals from last chapter, so think about those as we're doing these. So we're going to become very, very familiar with the sight of this expression right here, the sum from n equals 1 to infinity of stuff. A sub n is generic, but this is going to be our infinite sum. And we call this sum, this infinite sum, a series. When you add up the terms of a sequence, you get a series. Now, we can have a finite series, but we are almost always going to be talking about infinite series. And the big question for series is the exact same question as the big question for sequences. Namely, does it converge or does it diverge? And if it does converge, can we determine what it converges to? That is the number one question that we need to be able to answer in this chapter. Does the series converge or not? So what does it mean for a series to converge? Well, to answer that, we need to consider this thing called partial sums. So for example, we don't want to consider the infinite sum because that's too hard to wrap our brains around. So instead we're going to think about parts of the sum. So S sub 1 is going to be the sum of the first one term. In other words, is going to be the first term. S sub 2 is going to be the sum of the first two terms. In other words, A sub 1 plus A sub 2. S sub 3 is going to be the sum of the first three terms. S sub 4 is going to be the sum of the first four terms, etc. S sub n is going to be the sum of the first n terms. So we can actually create a sequence, S1, S2, S3, S4, S5, dot, 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 S sub n, dot, 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 and that infinite sequence of partial sums can either converge or diverge. And if the partial sums, the sequence of partial sums converges to a value, then we say the series converges to that value. So it's just a handy way of dealing with infinity. It's kind of like using limits to deal with your improper integrals. Instead of just, quote, plugging in infinity, you've got to use limits. This is kind of the same idea. All right, so all the stuff that I said is kind of explained in those words right there. You can pause the video and read that if you need to. But we're going to take a look at a few examples. Write the first few partial sums and determine if the series converges for each of these series. So this first one is the sum as n equals 1 to infinity of 1 over 2 to the n. So we can write this as 1 over 2 to the 1, that's the first n value, plus 1 over 2 to the 2, when n equals 2, and then we're going to let n equal 3, and then we're going to let n equal 4, and then we're going to let n equal a generic n, but we don't stop there. It's important that we don't stop because this says infinity, so I'll say plus dot dot dot, and that last plus dot 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 is important. You can lose points for leaving that off. So it should be clear that S sub 1 is 1 over 2, and S sub 2 is 1 over 2 plus the second term, which is 1 over 4, and S sub 3 is 1 over 2 plus 1 over 4 plus 1 over 8. S sub 4 is 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. I hope you get the idea. When we add these up, we get 1/2, we get 3/4, we get 7/8, we get 15 over 16, and you might see the pattern here. So we can say that S sub n is equal to the sequence 1/2, 3/4, 7/8, 15 over 16. You might notice that the denominator is always a power of 2. In fact, it's 2 to the 1, 2 to the 2, 2 to the 3. So that's 2 to the n. And then the numerator is always 1 less than the denominator. So it's 2 to the n minus 1. And if we can find that pattern, then we're cooking with gas here, because we can now say, well, what happens to this nth term? as n goes to infinity. And we know that the limit as n goes to infinity of this expression, well, that minus 1 doesn't really matter for extremely large values of n. We can pretty much ignore that, and we get 2 to the n over 2 to the n, which equals 1. So we can say that this infinite sum of values adds up to, eventually, 1, if you add them all up. Of course, there's no such thing as all of them, so we would say that the sum approaches 1. The farther we go along here, the closer we get to 1. We never actually exceed or even get to 1, but we can get arbitrarily close to 1. All right, so that is an example of a converging infinite series, not a sequence, but a series. Notice that the sequence of terms, 1/2, 1/4, 1/8, 1/16, the individual terms are approaching 0. But the sum of those positive terms, of course, is not going to approach 0 because we're adding up a whole bunch of positive values. It approaches the value 1. Alrighty, now let's take a look at our next infinite series. This is the sum from n equals 1 to infinity of 1. So our first term is 1, and our second term is 1, and our third term is 1. And we just keep on getting 1 over and over and over again. So if we look at the first several partial sums, s sub 1 equals, well, the first term is 1. S sub 2 equals the sum of the first two terms. 1 plus 1, last I checked, was 2. And s sub 3 is going to equal the sum of the first three terms. Well, that's 1 plus 1 plus 1, which is 3. It doesn't take too long to determine that the sequence of partial sums is going to be 1, 2, 3, etc. The nth partial sum is going to be n, and that's just going to keep on going on and on and on. And the limit as n approaches infinity of n is, well, it's infinity because n is approaching infinity, so n must be approaching infinity. Therefore, the series diverges to infinity. So we can see that sometimes our infinite series will converge to a value, sometimes they will diverge to infinity. This particular one is not a very exciting example. It's not very surprising that if we just keep on adding 1 over and over and over again, our sum will continue to grow without bound. So let's look at a more interesting one, and perhaps the most interesting of all the infinite series is this one right here. This is called the simple harmonic series, and I'm not going to spoil anything for you here, so don't look that up. Instead, let's just play around with it. This is, well, the first term is 1 over 1. The second term is 1 over 2. The third term is 1 over 3. The fourth term is 1 over 4, etc. And when we look at these partial sums, we're going to look at s sub 1, which is equal to 1, of course, s sub 2, which is equal to 1 plus 1/2, which is 3 halves, and s sub 3 is 1 plus 1/2 plus 1/3, which is going to be something. It's going to be 3 halves plus 1/3, which is going to be 9 plus 2 is 11 over 6. Okay, so this is small. This is a little bit bigger, still less than 2. And if we keep on going, we're going to get 11 over 6 plus 1/4. And let's see, 44 plus 6 is 50 over 24. Yeah, I could have found a smaller common denominator, but I'll just reduce this and get 25 over 12. Okay, so actually we're bigger than 2 now, right? This is less than 2. This is a little bit bigger than 2. But it certainly seems to be growing slowly. And the question is, how fast is this thing growing? And does this thing converge or not? So that's an interesting question, and we don't have the tools to answer this question just yet. So I'm going to put a big old fat question mark here because we don't know. Now, it can be fun to play around with Desmos, the best site in the world. And one nice thing we can do in Desmos is we can create a list. And I'm going to make that list K. I would use N, but N is a reserved variable for the sum. So you'll see that in a minute. So if I say that 1, 2, 3, 4, 5, all the way up to 100, I'm going to make this 100 element list of all the positive integers from 1 to 100. I'm going to plot these partial sums. uh, k comma the sum from n equals 1 to k of 1 over k. That doesn't look right. 1 over n. There we go. So this is when n equals 1. I know it's k now. So our first term, a sub 1, is 1. A sub 2 is 3 halves. A sub 3 is 5 sixths. A sub 4 is 25 twelfths. And that continues. The denominators get worse and worse and worse as we go along, so we're definitely going to want to use a calculator for all of these. In fact, instead of doing that, I can just click on label. Not very useful. But we can see that this graph is growing, and is growing slowly. And we can scroll over and we can ask the question, does this thing ever stop growing? Well, it doesn't stop growing, of course, but is there a limit to how high it will grow? And, we're all the way out to 100, and we're just now barely getting above 5. Okay? Now, if we change that to 1,000, yeah, it'll grow higher, but will it grow significantly higher, or is there some ceiling? And again, we don't know the answer to that question yet. More on that later. So let's consider one more sequence, let's consider one more series or sequence of partial sums in this video. We'll look at this one right here. This is similar to the last one. It's still a fraction, right? The first term is still 1. Instead of 1/2, we're going to square that 2 and get a 4. Instead of 1/3, we're going to square that 3 and get a 9, etc. And we're going to keep on adding those. Much like we saw before, these sums are going to be growing, and they're going to be growing kind of slowly, right? 1 plus 1/4 is 5/4. In fact, they're going to be growing even more slowly because, well, 1/4 and 1/9 and 1/16 show up in this series. We're missing a whole bunch of terms here, right? We're missing 1/2 and 1/3, 1/5, 1/6, 1/7, 1/8. A whole bunch of terms are left out here. Let's see, so 5/4 plus 1 over 9 is going to be 45 plus 4 is 49 over 36. Anyway, so S sub n equals 1 5/4, 49 36. And then again, this starts to get a little bit tedious, so I'm going to stop there and go back over to our favorite site, Desmos. And I'm going to look at, let's go home, and let's look at the related series. We're going to go from n equals 1 to k of this time 1 over n squared. And let's make it a more exciting color so we can kind of compare them there. And you can see for sure that this orange series, while it starts in the same place and grows slowly, grows much, much, much more slowly than the purple. Okay? And in fact, we can keep on going out, and it sure does appear as though it's not growing hardly at all. So unlike the purple, we have some pretty good evidence that the orange has some sort of upper limit. It doesn't seem like it's ever going to get above 2. Perhaps it will eventually if we go out to n equals 1,000,000, maybe. We'll see. I mean, we could try, right? We could see what happens when the sum from n equals 1 to 1,000,000, is that 6 zeros? Yeah. Of 1 over n to the second. Oh, no, it's still less than 2, right? In fact, it's barely bigger than this, and it's got almost 1,000,000 more terms than this. But all of those almost 1,000,000 terms are so itty-bitty that the 1.635 only goes up to a 1.645. So again, this is not a proof. We don't know for sure that this thing converges, but it sure does appear to converge. For the sake of right now, though, we're going to say maybe this converges. It appears to converge. More on that in the lessons to come.